Hey guys, we're going to get started in chapter 4, polynomial functions. This is going to be a 2-day lesson for 4.1. So let me present my screen and we'll get started. Okay, so there is a lot of notation and terminology that we're going to go over today. First, a polynomial, and this is review. You know polynomials from Algebra 1. A monomial or a sum of monomials. So the first example, this is a polynomial. We call it a binomial because there are two terms, 5x plus 2. Each one, this is a monomial, 5x, and 2 is a monomial. And then together, it's what we call a binomial, which is a type of polynomial. The next is another polynomial. It's a 3-term polynomial, so it's called a trinomial. All right, polynomial functions, a function of the form f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot, 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 where a sub n cannot equal 0. The exponents are all whole numbers, and this is important. They're all whole numbers, and the coefficients are all real numbers. All right, so an example of a polynomial function would be f of x equals 3x cubed plus 4x squared plus 2x minus 1. All right, and just a little bit more on the notation that I want you to add to your notes. All right. Okay, so just a little bit more to add. A sub n is your leading coefficient. N represents the degree. And a sub 0, that represents your constant term. All right, and then we have what's called end behavior of our polynomial functions. Let me scroll down just a little bit. So the end behavior of the graph of a function as x approaches positive infinity or negative infinity. So when we talk about the end behavior, we're talking about where the ends are going. Okay, the end of this graph is going up, up, and to the right. Right is slightly, it's going up and to the right as it keeps on moving. So it says f of x is approaching positive infinity as x is approaching positive infinity. Remember, think of f of x as your y. So it's going up and to the right. So up is positive y, to the right is positive x. So y is approaching positive infinity, right? The y's are going more positive as the x's are approaching positive infinity because the x's are continuing to get more positive, or not more positive, but positive. All right, the end behavior down here, think to yourself, it's going down and slightly to the left. So what's happening to your y values when they're going down? They're getting negative. All right, what's happening to your y values when, or not y, sorry, when you're moving to the left, what's happening to your x values, right? If you're moving along to the along the x value to the left, the x's are getting negative. So this says that y is approaching negative infinity because it's moving down, as x is approaching negative infinity because it's moving to the left, okay? So based on the end behavior, we can determine the degree of the polynomial function, and we can determine if the lead coefficient is positive or negative, okay? So to understand this, let's actually think back for a second to our quadratics, right? We just studied, oops, I need a pen. We just studied quadratic equations, right? F of x equals ax squared plus bx plus c. And we know when we graph our quadratics, it's a U-shape, it's a parabola. We could either have a parabola opening up or we could have a parabola going down, right? And we know that it opens up if our a value is positive. It opens down if our a value is negative. So think about that for a second. Okay, think about that for a second. Also notice the degree of this polynomial. We determined the degree of the polynomial by looking for the highest degree. The degree is 2, which is an even number. All right, so let's look at the degrees of the polynomial functions down here that also have even degrees. So, for example, these two as well. It says that this polynomial function is an even degree polynomial and its lead coefficient is positive. And here it's an even degree polynomial with a lead coefficient that's negative. So it actually models the shape of our parabolas. Notice this polynomial function, both ends are going up, and this polynomial function, both ends are going down. So when we, in a moment, look at other polynomial functions, okay, like for example, this one, the highest degree is 4. So I would say the degree of this polynomial is 4. And if it's an even number, right, it's going to look like one of these. If it has an even degree, both ends are going to face the same direction. Both ends are either going to go up or down. They're both going to go up if your lead coefficient's positive. They're both going to go down if your lead coefficient's negative. All right. The other polynomial functions that we're going to look at are odd degree polynomial functions. And when you have an odd degree polynomial function, so a polynomial function like x cubed or x to the 5th or x to the 7th, right? If the highest degree of the polynomial is cubed, a 3, 5, a 7, a 9, that's an odd degree. And in that case, the ends are going to be going in opposite directions. One end is going to go up, like you see here, while the other end is going down. All right, or it could have this end going up and this end going down. And to understand which one it models, I'm actually going to say, think about lines for a second, right? If I was to, instead of making this look, excuse me, like a polynomial function, if I was to kind of stretch it out, right? If you were to take this end and pull it down here and take this end, pull it down there and make it into a straight line, the slope of this line, does that slope or is that slope positive or negative? The slope is positive. So a polynomial function that takes this shape has an odd degree and a positive lead coefficient. If the polynomial function takes this shape, again, it's an odd degree because one end is going up while the other is going down. And if I was to stretch this out and make it into a line, notice that line would have a negative slope. So there's a negative lead coefficient. This might seem a little confusing now, but I'm hoping that it'll all make sense as we look at some examples. And then you can come back to this and then you'll be like, oh, I knew what she was talking about. Next thing that I have here for you are just some common polynomial functions, because you should know the names of them, okay? We talk a lot about linear functions. We're used to, here's an example of a linear function, a line, right? Y equals mx plus b. We just spent a whole chapter looking at quadratics where the highest degree is 2. So an example would be 2x squared plus x minus 9. That's a quadratic function. If the highest degree of the polynomial function is 3, we call it cubic. If the highest degree is 4, we call it quartic. I think that's as high as I make you know. Yeah, it looks like that's as high as we go. There are names for other polynomial functions, but that is as high as I'll have you guys memorize, I guess I'll say. All right, so next it says, decide whether the function is a polynomial function. If so, write it in standard form and state the degree, type, and lead coefficient. So before we get into the problem, let's go back to the vocabulary to talk about a polynomial function for a moment. A polynomial function, right, is written in this form where a of n cannot equal 0, and the exponents are all whole numbers and the coefficients are real numbers. So this is the important part. Exponents are whole numbers and coefficients are real numbers, no i's, no imaginaries, okay? So let's go down to the first problem and see if it fits. So before you determine whether it's a polynomial function, it's probably best to write it from highest degree to lowest. So ignore that. We have f of x equals highest degree is this term here, so negative 3x to the 4th. Then I go to my square term, so plus 2x squared. Then I go to my x term, so plus 6x, and then just the plus 1. Are all of the exponents whole numbers? They are. This has an exponent of a 1 if you want to write it. Are all of the coefficients reals? Do you see any imaginaries? They're all real numbers, right? -3 is a real number, 2 is a real number, 6 is a real number. So this is, yes, a polynomial function. So after you determine that it is, it says, if so, write it in standard form. We already did. This is standard form, highest exponent to lowest. State the degree. Okay, the degree, after you get it in standard form, is just the highest degree that you see. Degree is 4. Okay, then it says, state the type and the lead coefficient. So the type, what they're referring to there, let me scroll up, even though my writing's going to go with me for a second. They're talking about this right here. See, it says type. Is it constant? Is it linear? Is it quadratic, cubic, quartic? So since the highest degree is 4, we know that it is quartic. And finally, the lead coefficient, which I'm just going to abbreviate LC, the leading coefficient. Once you have it in standard form, the first number in front of the variable is your lead coefficient. So lead coefficient for this problem is -3. All right. All right, let's look at number 2. So number 2, writing it in standard form. So I have m of x equals highest exponent first, so -3/7 x cubed. And I have an x, but it's in the denominator. If I wanted to bring this up to the numerator, does anyone remember what's going to happen to the exponent? The exponent has to become a -1. And then, I can't see what I scribbled over. And then we have a -3 on the end. Okay, so is it a polynomial function? Does it have all coefficients that are real? Yep, they're all real numbers. Does it have all whole numbers for exponents? No, it does not, okay? -1 is not a whole number. So it's not a polynomial function because of negative exponent. All right. Okay, let's keep on scrolling down. Oh, more of the same. All right, so g of x equals, so the term with the variable is going to go first, √15x plus √5. Is this a polynomial function? Are the coefficients real numbers? They are. √15 is a real number. Remember, you just don't want an I, so you don't want a negative under a square root because that would be imaginary. And are the exponents whole numbers? Yep, the exponent on that x is just a 1. All right, so yes, it is a polynomial function. And we're asked to determine the degree, the type, and the lead coefficient. So the degree is 1. If you go back up to the chart, if you have degree 1, it is a linear function. And the lead coefficient is √15. All right. And the last problem, looking for the highest exponent first. So I have p of x equals -2x squared. Then comes the plus 3x. Then comes the -2√3. So are all the coefficients real? Yep, I don't see any i's. I don't see any negatives under radicals, so they're all real. Are all of the exponents whole numbers? Yep. So yes, it is a polynomial function. Oh, I'm off the screen. And then again, I'm looking for the degree, the type, and the lead coefficient. So the highest degree, once you have it in standard form, it's nice and easy, is 2. Degree 2 means it's what? Quadratic. And lead coefficient is -2. Okay. All right. The next set of problems, I bet that you know how to do without me even showing you how to do them. So think about the directions and think, if I wasn't here to help you, what would you do? It says evaluate the function for the given value of x. H of x equals -x cubed minus 2x squared minus 3x plus 4, and x equals 2. So what would you do to evaluate this function when x is equal to 2? You're just going to plug 2 in for each x that you see and simplify, okay? So this is a matter of order of operation. The left-hand side, this is just notation. The way we write this, h of 2, that's just telling the reader that we're evaluating this function when x is equal to 2. So it's negative, and then you always put whatever you're plugging in parentheses, 2 cubed minus 2 parentheses 2 squared minus 3 parentheses 2 plus 4. Those parentheses are super important, especially for this first part here. All right, so 2 cubed, 2 times 2 times 2 is an 8. And then you have that negative out front, so it's -8. Minus 2 times 2 squared is 4. Minus, we do the multiplication here, 6 plus 4. We still have one more multiplication step, so -8 minus 8 minus 6 plus 4. We work from left to right when we have addition subtraction. So we have -16 minus 6 plus 4, all right? -16 minus 6 is -22 plus 4. And then -22 plus 4 is going to give you a -18. So you would write h of 2 equals -18. Again, this notation is saying I evaluated the function at 2. I plugged 2 in for the function, and my output is -18. Okay. Let's do the next one. This time we're substituting in a -4. So left-hand side is just notation, g of -4. The right-hand side is where we do all of our work. -4 to the 4th minus 32 times -4 squared plus 256. Go through and take care of your exponents first. So -4 to the 4th is going to be a positive 256. All right, then you have minus 32. -4 squared is a positive 16 plus 256. Then you're going to do this multiplication step. So you're going to have 256. And when you multiply -32 times 16, you get -512 plus 256. All right, so when you take 256 and subtract 512, you're left with -256, and then bring down the plus 256, which gives you a 0. So g of -4 equals 0. Again, that says when I evaluated this function at -4, the output was 0. All right. All right, let's keep on moving along. I think we just have 3 more problems that I want to do tonight. So 7 and 8, describe the end behavior of the graph of the function. So this is where hopefully the chart up here will start making more sense. Okay, so follow along with me. So the first thing I'm going to do is have you make sure it's in standard form and tell me the degree and the lead coefficient. Okay, this is in standard form, so I can just look at it and I can see that my degree is 6 and my lead coefficient is -3. I actually don't even really care about the actual number. I really want to know for degree, is it even or odd? And for lead coefficient, is it positive or negative? So my degree is even and my lead coefficient is negative. As soon as I realize that my lead coefficient is even, I immediately start thinking about quadratics, because quadratics, right, have a degree of 2. So all of our quadratics or all of our polynomials that have an even degree are going to have ends facing up. And I don't really care exactly what the function looks like. I just want both ends up. or we're going to have both ends facing down. Okay. To determine is it this or that, that's when you move on to lead coefficient. If the lead coefficient's negative, think about your a value. When your polynomial function started with a negative value, what did that mean? It means that both ends are down, it's facing down, it reflects over the x-axis. So I know that, oops, I want to black. Since I have a negative lead coefficient, that means my polynomial function is going to look like this. Okay, so now what I'm going to do, I'm going to sketch that a little larger. Again, I don't really care if you just make it into one U or if you want to make it kind of like a, have multiple maxes and mins, is up to you. I just need both ends facing down because, again, it's an even degree negative lead coefficient. So then you're going to say to yourself, the y values are going down, right? This graph is going down over here, and it's slightly moving to the right at the same time. So y values are moving down, and x values are moving to the right. So when you move down on the y-axis, that means your y's are getting more negative. When you're moving to the right, that means your x's are getting more positive, okay? But the way we write this is we say f of x, the y values, are approaching negative infinity. So again, the y values are going down or getting more negative. The y values are approaching negative infinity as the x values, what are they doing? The x values are moving to the right. They're moving more positive. So they're approaching positive infinity. That is how you describe the end behavior for this end of the polynomial function. So now I need to move over and talk about this end, okay? Well, the y values are still going down, but it's going down and to the left. So y values down, which is negative, and the x values are moving left, which is negative. Okay, so how do I translate that into this notation? Y values, remember we say f of x is approaching, they're moving down, so negative infinity, as what's happening to the x values? They're moving to the left, which means they're approaching negative infinity as well. So this is how you describe the end behavior for the function over here. So again, the directions say to describe the end behavior of the graph of the function, I would be looking for these two things. All the rest is just my work to get me there, okay? So let's see if we can do number 8 a little more quickly. So for number 8, first thing you need to do for this one that we didn't have to do for the last one is write it in standard form, highest exponent to lowest. So f of x equals the highest exponent I see at x to the 5th. So it's 3x to the 5th. Then I'm going to move to my cube, so negative 3x cubed. Then I have actually 2. I wonder if that's a mistake. Hold on. Oh, it's not a mistake. I'm going to come out. It might be a mistake, but we'll just combine like terms. These are like terms, so we should really combine them, or they may have forgotten to put an exponent on one of them. Excuse me. In any case, and when I add them, I get 34 over 5x and then minus 2. All right. So from here, I see that my degree is a 5, which is odd. And my lead coefficient is a positive 3, which is positive. Again, for degree, I need to know even, odd. For lead coefficient, positive, negative. Then from there, since my degree is odd, it doesn't model a quadratic. It doesn't model a parabola where both ends are facing the same direction. So I know for this polynomial function, I'm either going to have a polynomial function that looks something like this, or I'm going to have a polynomial function that looks something like this. Now, again, I know that because of the fact that it's odd. Odd means the arms, the ends are going to go in opposite directions. To pick which one, I think about a line. Okay, Think back to Algebra 1 for a second. If I was to stretch this, right, instead of having these little lumps here, if I was to stretch it and make it a line, would this line have positive or negative slope? That line would have negative slope. If I was to stretch this one, it would have positive slope. Excuse me, I have a tickle in my throat and I don't want to cough into the headphones. So because my lead coefficient is positive, I want the polynomial function, I want the graph that if I was to stretch it out, the line would look like it would have positive slope. So I'm going to pick this one, okay? So, actually I'm going to draw it larger over here, but hopefully you have space on your paper. So now I need to talk about the end behaviors of this graph. Okay, so this end is going up and to the right. I'm not going to write all the same words I wrote for the last one. Try to make it a little more simplified. So up means positive infinity, to the right means positive infinity. So the y values, f of x, are going up. That means they're approaching positive infinity. As the x values are moving to the right, which means they're approaching positive infinity as well. So f of x is approaching positive infinity as x is approaching positive infinity. That's for this end of the graph. This end is moving down and to the left. So down means negative infinity. So f of x is approaching negative infinity as x moving to the left is also approaching negative infinity. So that's the end behavior for this side, this end of the graph. And again, these are the two answers to the problem. All the rest is just the work to help me get there. Okay. All right, last one. Describe the degree and lead coefficient of the polynomial using the graph. Describe doesn't mean tell me the exact number. Describe means positive, negative, even, odd. Okay, so let's talk about the degree first. And then we'll talk lead coefficient. So since my ends are not both going up and both going down, what does that tell you? Is the degree an even number or, yeah, so I want to say an even number or an odd number? The degree would have to be an odd number, okay? If it was even, it would look like a parabola, meaning both ends would face the same direction. All right, so I know that the degree of this polynomial is either a 3, a 5, a 7, a 9. It's an odd number. My lead coefficient, positive or negative. This is where you want to think about slope of a line, right? If I was to stretch this out and make it look like a straight line. That was terrible. I don't know why I didn't use my pen to draw that line. Sorry, let me try that again. If I was to stretch this out and make it look like a line, right? Would that line have positive or negative slope? It would have negative slope. So that means that the lead coefficient is negative, okay? So the degree is odd, the lead coefficient is negative, right? And that, I believe, is all I want to do for day one. Let me get my mouse, go back here. We will finish this lesson up and do the graphing portion of it in day 2, the next time I see you. All right, bye.